Hi everyone, welcome to 3 Minutes Engineering Concept. The idea of this channel is to explain any fundamental to advanced mechanical engineering and material science related concept in 3 minutes time. If you like the idea, then please like, share and subscribe to our channel so that you can get regular updates. Also, please share the link of our YouTube channel and also Facebook page with colleagues and students who can really benefit from it. Thank you very much. Okay, so in today's short video, people have asked me to explain how they can estimate the potential wind resource or wind characteristic of a certain area, which might be useful in selecting a site for a potential wind farm or wind turbine. So in this short video, I will tell you in an ideal world how you can estimate power which is there in a wind in a certain area. In order to understand this concept, we need to revisit our basic fluid mechanics. So imagine this is our wind turbine here in this area, and our wind is flying across this wind turbine rotor, which may be rotating. In this case, we just say it's a control volume. So we just assume that wind is gonna have a velocity u, and it is traveling in this direction as I showed you here, and the cross-sectional area of my wind turbine rotor or any control volume is A. So based on my basic fluid mechanics, for mass flow of air through a rotor disc of area A is computed using this relationship where my change in mass with respect to time is density times the area times the average wind speed. So I can give my mass flow rate m dot as this relationship, and now if I go back to my basic mechanics or physics, the kinetic energy per unit time is the power, or energy per unit time is power. So power is given by kinetic energy over time, and kinetic energy is half of half times m times the velocity square as per the Newton's law of motion. And then if I use dm over dt, then this is over time, so this becomes power. So that's why I call kinetic energy per unit time here. And if I replace my dm over dt with this relationship here, then I have a relationship for power which is half rho a u cube. So based on this relationship, I can estimate the power in my wind resource if I know the velocity of it. If I assume that the density is constant and area I know, which is the area of this rotor here, and if I know the velocity of wind, then I can see that it's a cubic function of the speed of wind in this case. So what I do is, in the real world, when I have wind turbine, or if I'm selecting a wind turbine, I can have many options in which I can have different areas depending on the diameter of the rotor blades, right? So I would try to come up with some kind of quantity where my wind power is independent of this area. So what I do, I just take this on the other side and I will call this power per unit area, or sometimes people use the term wind power density in many textbooks. So wind power density is nothing else but it's the same relationship here, but you just remove the area and you take it on the other side, and that's why you have half of rho u cube. So now if I assume my density of air to be constant for the certain region, let's say if I say it's 1.225 kilograms per meter cube, so for different wind speeds I can estimate what is the power density for that specific area for different speeds. And you can see it's a cubic function, so it increases very drastically due to the cube. And power density concept is very important because now you are independent of the wind turbine rotor, because right now you are still working with the potential site. So it could be to estimate how much how much power you can produce at a certain site. So if you have, let's say, data for 3 different sites for the wind velocities, then you can compute the power density, and then you can basically see which is the best site. So what you do is you compute the power density, and as a thumb rule, this is one of the thumb rule I have given you, but there are many different standards, many different ways of doing it. So if your power density is below 100 watts per meter square, then it's a low potential site. If it's around 400 watts per meter square, it's a good site. If you get a power density of over 700 watt per meter square, then it's a great site. So this is, again, these values are just ballpark figures and they may change from one book to another book, one area to another area. So this slide is just to give you a quick example on how you can use that power density relationship to see which site is the best or most suitable site for your wind farm. So if you're working in industry, or if you're working for a design consultancy for wind farm design or something like that, then let's say you get the data, which could be of a graphical form, or it could be many tables in the Excel. So you can use that, and you can basically find out or estimate the power density using a simple relationship, which is a starting point. So let's say in this case we have 3 sites and we need to find out which is the best one for us. So what I would do, I would read all the values using some digitizer for each site. In this case I have read the values for site 1. I will find the average wind speed for the whole year, and then I can find out the average power density of that area using this relationship, which comes out to be this. Now what I will do, I will repeat the same for site 2 and site 3, and obviously in normal terms, whichever has the highest power density will be the best suitable site. And then you will be now thinking, okay, why do I need to do that if I can see that this site has already higher velocities throughout the year? But maybe this is not the only thing you have to see in real life. It's more complicated. Maybe at this time of the year you might need more power in the grid, or your load is very high. So maybe this site might not be suitable for this, which is the critical time of the year. So in that case, maybe site 2 might be more better option, or much better option than site 1. So there are many different factors which are also influence your decision. It's not only one of these things. So again, you have to be in the practical world, it's more complicated, but this is one of the basic way of doing it. Other than that, I think you can also use many different types of statistical model. This is one example here. In this case, if let's say if you are given hourly data for many years, generally they say that if you need to get a good average of power density of wind resource, you need to get 15 to 30 years data for that site. So if you have that kind of data, then you can use different types of statistical model. In this case, I have shown you one where again the relationship is the same. Power density is half rho times average annual speed cube, but there's an energy pattern factor KE here, and this factor is basically to take into account the whole data for all those 30 years of hourly data or something. So this is the hourly wind speed, this is the average annual speed, and this is the total number of hours for which you add everything together, and this gives you that factor. You take it there, and that will give you a kind of a statistical response of the whole thing. Again, this is a very simplified model. There are more complicated models available, and you can look into the literature for that. So I hope this video makes sense, that how to estimate what sort of power is stored in your wind resource for a specific site, which might be helpful to see if the site may be suitable or not for your wind turbine or wind farm.